All right, so yeah, thanks Nathan for this opportunity. Yeah, so today I want to give an overview of recent works that I've been doing. And I think what I want to focus today is in this title here. So I want to focus on some application of machine learning concepts to many-body physics. Okay, so let me start with like the overall view. So basically, I'm interested here in system of many particles. Okay, and the key ingredient here is like the strong interactions between these particles, mainly systems that are in a quantum regime. Okay, so here I mentioned some examples of, let's say, many-body systems. So like materials like high-TC cuprates, synthetic quantum system, and also quantum computers. And one aspect that I want to emphasize now is, so in order to study the properties of the system, we have to solve the many-body problem. Okay. So basically what we typically do is we consider a lattice model, a simple model that incorporate like that has the interactions, the main ingredient, okay, but it's there are not so many ingredients in the model. So then you try to study, like, for example, thermodynamic properties or dynamics properties of this model. Okay, but the problem is that in order to solve this the Schrödinger equation for this model and study these properties, we need to solve a problem that is very hard. Okay, so basically, one aspect that why this problem is very hard is that if you want to solve this problem numerically, let's say in a classical computer, we need to, in order to build the Hamiltonian of the system, we have to store the number of elements that we have to store typically is of the order of 2 to the power of, it's like exponential number, okay? It increase exponentially with size of the system. So in that sense, it's an exponentially difficult problem to solve. So this is one aspect that I want to stress. And the other aspect is that even when you know how to solve the problem, I mean, even when you are able to write down the wave function or to store in the classical computer the wave function of the system, another non-trivial question is how to characterize the system, how to determine in which phase this system, this state is, or if the system is close to a critical point or not. Okay, so this is another aspect. So basically, so here is a summary of the topics that I want to address today and tomorrow. So the basic 2 questions that, let's say the basic 2 problems that I'm interested in is to implement and develop numerical tools to solve the many-body problem. I mean, to overcome this the exponential complexity. Okay? And the other problem is to characterize phase of matter and phase transition. Okay? And the key aspect is that of the things that I will talk here is that this I use like concepts of many that are in the intersection between many-body physics and quantum information, or many-body physics and machine learning. So I use these concepts like entanglement and these 2 concepts in the context of machine learning, this concept of intrinsic dimension in neuroquantum states. Okay? So more specifically today, we will focus in this part. Okay? For that reason, I put the title machine learning. So basically, I want to explore 2 problems here. I want to tell you about 2 problems that I recently worked on. So the first one is related to the characterization of phase transition with this concept of intrinsic dimension, okay, that I will discuss later what this is. So the basic idea is to try to extract universal quantities from raw physical data sets. Okay? And in the second part of the talk, I will discuss a bit about this recent ansatz, many-body quantum state ansatz that is called neural quantum states. And more specifically, I'm focused on in studying dynamics of many-body system using this approach. All right, so basically the outline of my talk, I split my talk in 3 parts. Okay? The first part, I want to discuss a bit more about the physical system that I'm interested in, this synthetic quantum systems. And I also want to briefly mention other works that I did that was related to these kind of systems. And then in the other 2 parts of the talk, I will discuss this machine learning part. Okay. All right. So basically, the kind of system that I'm interested in, as I said, there's a strong correlated system. Okay. So the basic idea of these synthetic quantum systems is that it's possible nowadays to manipulate quantum systems. Okay. So one example are ultra cold atoms, okay, trapped in optical lattice or in optical tweezers. And one aspect of these let's say experiments, these systems, is that the system are in a quantum regime, okay, a regime where quantum effects are important, like quantum degeneracy, Bose-Einstein condensation, and a regime where interaction between the particles are important. Okay, so and another aspect about this, let's say, these synthetic quantum systems, these experiments, is tunability. So the idea is that one can control parameters of the experiments, like interaction, and also the lattice. Like one can build a certain lattice where this atom sits. Okay? So the idea is that one can really realize quantum models in these experiments, like Ising-like models, Hamiltonians, or Hubbard-like Hamiltonians. So in that sense, this system can be seen as a quantum simulator. So one can use this system to address questions like how is the ground state of the Hubbard model, for example, in certain regimes of parameter, that cannot be resolved with other techniques, like with numerical techniques using a classical computer, for instance. So yeah, so basically this is, so there are other questions. So basically nowadays people try to like realize quantum anyibody phase and phase transitions in the system. Another interesting direction of these experiments is to realize, like prepare an initial state, non-arbitrary state, and then let this state evolve in a coherent way. Okay? So another aspect that I didn't mention, that this system are a closed system. Okay, so all right, so yeah, just to give an idea, so one of the works that I've been doing, like since my PhD here in Brazil, UFRJ, is to use numerical simulations like quantum Monte Carlo or even exact diagonalization to solve models for synthetic quantum systems. Okay? So here I'm just, I won't enter in the details of these works, but it's just to mention that so one key aspect of this work is that we try to raise like phase diagrams, ground state phase diagrams, temperature equal to 0 phase diagrams of these models. And one theoretical interest these works is to study quantum phase transitions. Okay, so but I don't want to focus on these works. Here is just to mention one aspect of my works, the works that I've been doing since my PhD. So let me mention another aspect of these experiments. Okay, so one is tunability, and the other one is the possibility to probe local properties and also quantum correlations, okay, like entanglement. So more specifically, so I also want to focus on entanglement. So there's also an important aspect of my work. So nowadays it's possible to measure like entanglement measures, like so entanglement is a quantum correlation without classical analog. Okay, so this system, one can measure the like entanglement measures in these systems. Okay, nowadays. Of course, there are like different. It's not an easy task. Okay, so one difficult thing about this kind of experiment is that very difficult to scale up this measure of entanglement. Okay, so typically people measure entanglement of a subsystem between a subsystem and the rest of the system, but the subsystem is not so large. Okay. It's exponentially hard to increase this size. So this is another topic that I will discuss tomorrow, in fact. So it's about entanglement. So it's more specifically, I want to discuss a bit about what is known as entanglement Hamiltonian. Okay. And how to probe entanglement, how to, let's say, measure entanglement via thermodynamics using this concept of entanglement Hamiltonian. Okay? So measure means both in numerical simulations and also in like some let's say also in experiments. Okay? All right, so now before I enter in the, let's say, machine learning part, let me mention some, let's say, state-of-the-art experiments about synthetic quantum systems. Okay, so here I mentioned these two papers. So these two papers, they simulate using this platform, this Rydberg atom platform, a 2D quantum system. So basically, they simulate the 2D quantum Ising model, okay? And they can realize the 2D antiferromagnet. That is let's say the ground state of this model. Okay? And one important aspect of this experiment is that they can probe locally. So here's a lattice. Each point here, each bright point here represents, let's say, a spin up. Okay? So here it is really an image. You can say that it's a wave function snapshot. Okay? So here we can really measure local properties and probe, for example, the magnetization of the system. Okay? So we can really detect that the system is in this 2D antiferromagnetic state. Right. So the work that I want to discuss this now, so the basic motivation of the work, is to try to design new tools to characterize quantum correlations. Let's say correlations. We also talk about classical systems in many-body systems, okay? Using machine learning techniques, okay, concepts. All right. So now let me start the second part of the talk. So the title is Unsupervised Learning Critical Phenomena via this concept of intrinsic dimension that I want to explain. I will explain more detail. So this work was done during my first postdoc at ICTP in Dresden. So basically, I will talk about these two works. So the first work is just classical. I will just consider like classical phase transitions, like thermal phase transitions. Okay, so then I will consider classical models. And in the second part, you also consider quantum phase transitions, and then I will also consider quantum models. Okay. These models, again, are motivated by the experience that I mentioned before in the first part. All right. Okay, so the first thing that I will try to do is to try to give you an idea what is this intrinsic dimension. Okay, so basically, when you talk about machine learning, usually we start like talking about data sets. Okay, so machine learning are like techniques to deal with large data sets. So here I mentioned two kinds of data sets, like handwriting data sets and also physical data sets, like the wave function snapshots that I mentioned before that can be measured in these experiments. So here are like Ising snapshots that are simulated in a classical computer, like using Monte Carlo. Okay? So the idea of machine learning is to try to, for example, to do image recognition of these handwritten data sets. But in a more abstract way, these data sets can be think as like points living in a high dimensional space. Okay? So basically, we can see this square here is a L by L lattice, and in each side of the lattice, I have 0 and 1, spin up or spin down. So each let's say each configuration here is a point in a high dimensional space. Okay? So now let me explain this concept of intrinsic dimension. So the basic idea is that typically for real data sets, so the data set, despite it's embedded in a space that has dimension that is equal to the number of coordinates. So here in this example, I mentioned a data set that's embedded in 3 dimensions. Okay? So the idea is that real data sets lives in a manifold, okay, that has a dimension, an effective dimension, which we call intrinsic dimension, that is lower than the number of coordinates. Okay? So here I mentioned this like just an example. So this is a Klein bottle data set. So these are points that I generate with a probability distribution. And the basic idea is that I can put this data set on a surface, okay, that is twisted, but it's a 2D surface. Okay? 2D. So the basic idea of intrinsic dimension is that. Okay? So this happens because real data sets, they are correlated. There are correlation between these points. Okay? And what I want to do here is to explore this concept of intrinsic dimension for physical data sets. So now let me return to these physical data sets and to be more precise how you define these physical data sets. So what we focus is this what we call partition function data set. So So my data sets are like configurations of a partition function. Here, again, I mentioned a classical system. So E is the energy of the system. So it can be like Ising model. Let's consider the Ising model as a. So the basic idea is that I can, for a given temperature, so beta is the inverse of the temperature, I can generate a bunch of configurations with Monte Carlo, for example, and then I can investigate how is the intrinsic dimension of this. So let me, and again, these data sets are like points living a high dimensional space. So let me show an example that you still can visualize. Okay, so this example has 3 spins. Okay, so it's a 3-spin XY model. Okay. And here I show the data structure of a system that has a temperature that is very low, like 0 temperature, essentially 0 temperature. And what I do is sample this configuration. Each point here is a sample that I get in my Monte Carlo simulations. Okay. And one aspect here that is already with this simple example that we see is that the data structure that you have in configuration space is very different, like 0 temperature and infinite temperature. So more specifically, if you use this let's say hand wave idea of intrinsic dimension that I tried to give before. So basically here you have the intrinsic dimension is equal to 1, and here the intrinsic dimension is equal to 3, okay? The number of coordinates. So basically the intrinsic dimension is the minimal number of minimum number of degrees of freedom that I need to describe my system. Okay? So at T equals 0 temperature, I just need 1 angle, okay? Because my system is ordered. So it's a ferromagnetic order. Instead, at high temperature, I need the 3 angles to describe my system. So the intrinsic dimension is equal to 2. Of course, this is just a hand wave. It's just an intuition, to give an intuition. What is this intrinsic dimension? How, let's say, physical data sets, how is the physical, the intrinsic dimension of physical data sets. But what we really did in this work, it was to study like physical data sets emerging in the vicinity of a phase transition. Okay, so the idea is that I have a thermal phase transition. Okay, so on one side of the transition, I have a disordered phase, and in the other side, I have an ordered phase, like a symmetry broken phase or a topological phase. And then how is the intrinsic dimension? So the basic questions that you raise is this: if you have like a kind of phase transition configuration space, and if you can extract information of the system from raw physical data sets, okay? More specific universal properties. Okay, so and then why we want to do this? So one can try to draw other reasons, but one reason is that the idea is that this question, which physical quantity to measure to probe a phase transition, is not a trivial question. Okay, so basically there are like phase transitions that cannot be characterized by local order parameters. So here we just use raw data sets and try to extract the physics from these raw data sets. So this is one motivation.
So what intrinsic dimension is always an integer or not?
No. The way that I will define here, no. So later I will try to explain a bit the method that we use to compute this intrinsic dimension. And in this case, it's not integer. It can be a non-integer.
Okay, you'll define it later.
Yeah, exactly.
Is this going to be related to the fractal dimension eventually? Because this data, these clusters, say, of overturned spins, say, in an Ising phase transition, as you approach the critical point, they become fractals.
Yeah, but they become fractals in real space, right?
They are
so here,
yes. They are
so here
embedding space, yes.
Yeah.
So intrinsic dimension is related to that or not?
So it depends how we define this intrinsic dimension. So we can define the intrinsic, you can measure, let's say, in other words, it depends how you measure this intrinsic dimension, how you estimate this intrinsic dimension. We can estimate this intrinsic dimension in certain regimes using the same methods that we use to estimate this fractal dimension, like this box counting, using this box counting. So if you use this estimation, yes, it will be equivalent to the fractal dimension. But we use another method. And using this method is not trivial to say that in certain regimes, yes, it will be equal to the fractal dimension, but like for the kind of
just one comment about it. It seems to me that what you define as your intrinsic dimension is like it's been defined in nonlinear dynamics as embedded dimension. What's the difference?
Yeah, so I just wanted to give you an intuition. I didn't define yet the intrinsic dimension, but so the basic idea is that the embedded dimension is equal to the number of coordinates of your configuration. So here, the number of coordinates is equal to 3. Okay, so this is the embedded dimension. The intrinsic dimension is like this effective dimension where my data set lies in. Okay, so here that lies in a line. Okay, so then the intrinsic dimension is equal to 1. But here you cannot lie this data set in a line. You really need the 3 coordinates to describe the data set. Okay, if there is no more question, let me just.
Here we go.
Yeah, okay, thank you. So let me just mention that this kind of problem was already studied, trying to extract physics from data sets, from physical data sets. So in fact, I think the first works that using machine learning to physics was trying to do something similar to what we are trying to do here, like to try to, let's say, characterize data sets, like for example, using an artificial neural network. So the basic idea, you can train this artificial neural network in such a way that if you pass to this artificial neural network Ising configuration, it will give you Faro or disorder states. So you can classify these states. But here you need to train this neural network. So you need to use labeled configurations. There are also interesting works that was published more or less at the same time of this work that use unsupervised approach. So the idea is that here we don't use any kind of labels for the configuration. You try to extract physics from the structure of the data set. Okay? Of course, this data set is very complicated, it's high dimension, and then you cannot see anything. But the basic idea of these works try to use some kind of dimension reduction of this high dimensional space, and then try to see some feature in this space. So here, for example, our data sets, Ising data sets, and the basic idea is that in the order phase, you have clustering, like 2 clusters in the order phase. So you can, but what you want to do is to try to do unsupervised learning without any kind of dimension reduction. So this is the novelty of our work, I think, compared to this previous work. So there is no compression, any kind of compression of the data sets. So yeah, now let me try to give you an idea of how to estimate this intrinsic dimension. And then I will show some results of classical and quantum phase transitions. So yeah, the basic ingredient, so basically, yeah, the basic ingredient to compute this intrinsic dimension is distance in configuration space. More specifically, for each point in the configuration space, you compute the first and second nearest neighbor distance. Okay? And this distance is defined using conventional distance, like Euclidean distance or Hamming distance. And the method that we use is called 2NN, so it's 2 nearest neighbor estimator. It was published in this paper. So the basic idea is that one can derive, so I won't explain how to derive this equation, but one can show that under certain conditions, the probability distribution of this quantity here, mu, that is the relation of the second and the first nearest neighbor distance, okay, is a function of this intrinsic dimension. Okay. So there are a lot of assumptions. There are, the main one is that the data set is locally uniform in density. Okay. So one can then derive this probability distribution that's called a Pareto distribution. Okay. And then what we do is to, in practice, to compute the intrinsic dimension is that we fit our empirical data to this formula. So this is how we compute this intrinsic dimension.
Yeah, I have a question. To be more specific, what do you mean by nearest and next nearest neighbor? You mean the expectation value in your data set?
It's function? So here is we are really looking to the distribution. So for each point, we compute like the first and the second nearest neighbor in configuration space. Okay? So it's really the distribution, the whole distribution. So let's suppose that you have, let's say, 20 points in my data set. So then I have 20 first nearest neighbor distribution. So for each point, I have the first nearest neighbor and 20 second nearest neighbor.
So these are nearest neighbors in the real lattice?
No, in configuration space.
So how do you define nearest neighbor in configuration space?
Yeah, so basically this one can be an issue, okay? So, but we just compute the Euclidean distance. So here, unfortunately, I didn't put the definition.
So you take two configurations essentially, and then you try to figure out what the distance between the configurations is?
Yeah. So basically, yeah, you have vectors, right? So my configuration are vectors. So I can compute distance between these vectors, right? Like just using the Euclidean distance.
In the configuration space.
Exactly, yeah.
Okay. Thank you.
Sorry, I also have a related question, so I missed that. So what do you call here configuration space? So can you give, what would be the configuration space for your Ising model? Just one of the spin-up, spin-down configuration?
No, the configuration space is like the space formed by the, let's return a bit, by these vectors here, right? So basically, let's like when I do a Monte Carlo simulation, I generate these configurations, right? For a given temperature, I generate this configuration. So what I call configuration space is like the space that's formed by this set of vectors.
Okay.
All right. So I don't know how much time I have, but okay. So yeah. So basically, let me. Of course, I would have to spend much more time to give all the details of this method, this 2n method. But here, the basic idea, as I said, that we fit the formula that I showed before. So here in the example, so here's like this t equals 0 example, and then you can have the intrinsic dimension equal to 1. And here, okay. So one aspect of this method, let me just emphasize two aspects of this method. The first is that there's a local feature of configuration space. Okay. So I'm really probing the intrinsic dimension locally. Okay. And the second aspect is that this intrinsic dimension depends on the typical value of this distance. Okay. So in other words, it's a scale-dependent quantity. Okay. So basically, the number of points in my data set, you affect the intrinsic dimension. Because if I put more points in my data set, I change the scale where I'm probing the intrinsic dimension. But this is a bit of technical detail that it's important to understand the results, but at this point we can go on. And let me show the results. Okay, so basically what I did was to study different kinds of phase transitions, classical phase transitions. Okay, so then I use my Monte Carlo and generate like 50,000 configurations at a given temperature. And then I compute the intrinsic dimension of this configuration. So this is what I did, what we did. So let me start with the simplest model, is the 2D Ising model. So, so basically, let me show the results. So here's it's an example of an example of a second order phase transition. Okay, so here's the result of the intrinsic dimension as a function of temperature. So the main feature that we observe is that near the phase transition, there is a minimum of the, so here are results for different system size. Okay? L is the linear size of the system. And the main result is that we observe a minimum, a local minimum in this intrinsic dimension at the temperature T star. Okay? But when we increase the size of the system, this minimum, numerically, you see that this minimum shifts towards the critical point. So what we did was to do exactly what we do with physical quantities like magnetization or susceptibility. We try to use a finite size scaling. Okay, so the basic idea is that in this case we know that the correlation length diverge this way, okay, close to the critical point, and then we can propose a finite size scaling. Then what you can do from this finite size scaling analysis is that you can compute critical exponents. And the critical temperature, and the critical exponents that we obtain is within error bars is equal to the exact one for the Ising model. Okay, so basically
Can you explain what physical quantity does the this effective dimension actually measures? Because you're using the same finite size scaling answer, the correlation length. So how do you know that is correct?
Yeah, so this is just empirical results, okay? So later,
Well,
actually, I didn't put this.
It must have some basis.
Yeah, exactly. Yeah, so basically, we try to explain this. And the basic idea is that we can relate the intrinsic dimension to correlation functions, okay? This is the reason why we believe this is actually a risk argument that you have, that you can relate the intrinsic dimension to correlation functions, okay, to many-body correlation functions.
Okay, which correlation?
But a priori, like in principle, like many-body correlation function, not just two-body, but let's say 3 or 4 body correlation.
Well, but the scaling behavior of these different correlators at the critical point is quite different. They are not simply related to each other. We know how they behave. Okay. In the case of the two-dimensional Ising model, this is well understood. So we know what the 4-point function, how it scales. We know how the 2-point function scales, and a few things.
Yeah. So later on, I can maybe try to give you this argument. But so far, it's more heuristic. So it's more like.
No, but the question is, okay, I don't care if it is heuristic. The question is, what do you expect this effective dimension to be a measure of?
Yeah, as a measure of correlations. As a measure of correlations.
Of what correlation?
I cannot precise you. So in our argument, we cannot define which specific correlation is. But
is there an expression that tells me that this actually is dominated by the 2-point function or the 4-point function? Or you need to return to the 23-point function?
Yeah.
This is a question.
Yeah, I have on a slide to this, but it's in the end, I didn't put in the main presentation. Maybe I can go.
Don't do that.
Okay, let me show all the results, and then maybe you can return to this point. But
I'd like to know physically what.
Yeah, my answer is related to physical correlations, but I don't know how to precisely which correlations, and I can give you my risk argument to explain this. But so far, I just have a risk argument. I don't have a precise argument to say which correlation, like to write analytically an expression that connects the ID with like correlations. Okay, this is my answer. All right. So yeah. So then, so again, we simulate other models. So much more models. But let me show another example. This is the 2D XY model. So here is an example of let's say a BKT phase transition, topological phase transition. Okay. And again, what we observe is the similar results that you have before. So we have this kind of minimum that increase, becomes more pronounced as we increase the system size. And again, so here, of course, we know to characterize the transition. We know how the correlation length diverges, and then we can use these to try to establish, let's say, finite size scaling for these quantities. And what we see is that if we assume that we can get good results for the critical temperature, okay, in this case, and also have the data collapse of the intrinsic.
So let me rephrase my question a different way. Suppose you didn't know what the universality class of a particular model is. How do you know how to scale your data?
Yeah, so basically, yeah, so but this is what happens with physical quantities.
I mean,
right?
this is an example where it's more subtle.
Yeah.
Because...
So for example, for 2D, for the second order phase transition, you also consider like transitions belongs to order universality class, like the 3-state Potts model. And in this case, the critical exponent is different from 1. Okay? So you can really compute this critical exponent. So it's like we can do finite size scale. From the finite size scale analysis, of course, you have to have good data, good numerical data. We can compute the critical exponent. So we can, like posteriori, define, establish which universality class the system, the phase transition belongs. Okay, so we studied the 2D Ising model, but also the 3-state Potts model. And for the 3-state Potts model, the critical exponents is different. It's I don't remember exactly the value, but it's different for 1. So it's so this is how we. Of course, for BKT, it's much more difficult because we have a correlation length that diverges much faster. as we approach the critical point. So it's numerically is more challenging to. We also, yeah, so just to finish, we also consider like first order phase transitions, and you have similar behavior. The difference that like in this case, this intrinsic dimension also has a minimum as we increase the system size, but for like say L equal to 90, we already have like a peak very close to the critical point. And one aspect is that we can also try to scale this minimum. And what we observe is that when you put in the scaling the dimension, like the trivial exponent, in this case, not a critical exponent, it's a trivial exponent, we get like within error bars, we get the exact value for the temperature. So our numerical results, it's also indicating that in this case, we are like, so the intrinsic dimension is following the scaling expected for a first order transition. That in this case is given by this trivial exponent. All right, so this is the main results that I wanted to show for the classical part. We also try to explore these for the quantum phase transitions. Okay? So, but for the quantum phase transitions, it's a bit more difficult because we have to define, it's a bit more difficult how you define these quantum data sets in this case. So basically what we do is exactly what we do in quantum Monte Carlo. Okay? So we map the quantum partition function in a classical partition function. Okay? So we can use, for example, path integral. We also use stochastic series expansion mapping that I didn't mention here. But the basic idea is that now, like for example, if you have a 1D system, when I do this mapping, I have an extra dimension. It's called an imaginary time dimension. So then I have this time slice. Okay? So in the data set, in this case, it's composed by certain slice of this, let's say, path integral configuration. Okay. So, but here I won't enter in the details, but just to mention that if I use these data sets, defined in this way, we have similar results for the classical case. So here, let me mention two examples. So here it's a 1D quantizing model. So here is the intrinsic dimension as a function of, like, here is not temperature anymore. So temperature here is equal to 0. So you just have quantum fluctuations. And H is the transverse field that induced this quantum critical point, this quantum phase transition. But I also have this minimum. Okay? And this minimum shifts towards the critical point. And one can, again, try to extract the, all right. Yeah, so this is the quantum part. I will try tomorrow to give more details. But this is more or less what I wanted to say about these parts of the talk. So the basic idea is that results indicates that the universal critical behavior of critical points can be learned through this property of data sets that we call intrinsic dimension. All right. All right. So now let me try to mention another direction that I'm interested in. And here, so here again, I want to try to use some machine learning techniques to, let's say, to shed light in many-body problems. But here the idea is let's say, it's completely different from the previous work in the sense that, so in the previous work, I had to solve my many-body problem, right? I have to solve my many-body problem with Monte Carlo or quantum Monte Carlo, and then I generate these data sets, and then I analyze this data set with this intrinsic dimension. But I had to solve the many-body problem. And here, it's one idea that was proposed like 5 years ago, more or less. The idea is to try to solve the many-body problem with this concept of using as an element of my method this artificial neural network. So there is no data here. Okay, so the idea is really solve the many-body problem. So,
Belita, do you have a question? You have your hand up. Belita, you're muted.
I have to ask him a question at the end.
Okay, so we'll wait at the end. Sorry. Go ahead, Tiago.
Yeah, exactly. So I just wanted to stress that here it's let's say it's a different approach. So here the goal is to really solve the many-body problem. And this work I started like more recently. So this is not finished work yet. I just show partial results. But I started this work the beginning of this year, when I started my second postdoc at the Max Planck Institute in Dresden. So here the goal is to study dynamics of many-body system using this concept of neuroquantum states. And more specifically, like, let me just, what is the physical kind of problems that I'm interested in? So basically, one of the problems is motivated by this synthetic quantum system. So basically, the system can be used to generalize coherent dynamics. So you prepare a system in a certain state and then let this state evolve. There are like some fundamental questions that we can raise, like how a closed quantum system reach or fails to reach a thermal equilibrium. And another interesting, another direction is that with dynamics, we can also compute dynamical response functions and connect with experiments and also many-body excitation. So in fact, today I want to focus on this part. Okay? I want to try to use this neuroquantum state and propose a method to compute dynamical response functions like ring functions. And the key idea is that what we want to do is that, so basically, typically what you want to do is, for example, compute the ground state of a many-body Hamiltonian, or compute the time evolution of our initial state. That can be an arbitrary state. But for this, we need to, of course, solve the many-body problem. And here the idea is, and then the problem is that my wave function is, in principle, it's the number of parameters that I have to store in my computer to have my wave function. In principle, it's very large. It's exponentially large. For arbitrary states, it's exponentially large with system size. So this is the many-body problem that I mentioned in the beginning. And then one important question in numerical physics for many-body system is like how to derive like efficient representation for the wave function. Okay, like let's say a function that depends on a certain number of parameters, okay? But this number of parameters is not exponential, it's polynomial, let's say. This would be already, it's polynomial with system size. Okay? This would be like the goal, okay? And there are like different methods, different kind of efficient like representations for the wave function. One that is very famous is like tensor network quantum states, okay? That use like physical information about the system, like the structure of the entanglement, as an insight to derive like how will be this efficient representation. And this kind of method typically works very well for low entangled state, but for high entangled state, this like 2D states, like in 2 dimensions where entanglement is higher, this kind of method tends to be more difficult to use this method, despite you still can use in some cases. And the idea of this to use neural network is exactly that, to use neural network as an efficient representation of, this is let's say the hope, right? And the idea is that a neural network is like these high dimensional functions. I won't explain, I won't give you all the details of this, but the idea is that it's like these models for high dimensional functions. And in principle, one can, this is like a universal function approximator, okay? Of course, it depends on the number of parameters that I have, but in principle, if I'm able to increase the size of my network, I can represent any function. And the basic element of this is each layer of network is a set of linear transformations followed by a nonlinear transformation. Okay. And yeah, and again, as I said, so this was inspired by this paper that was published 5 years ago, more or less, by Giuseppe Carleo and Matthias Troia, that they proposed to use these neural networks, more specifically, the simplest neural networks that is like a single layer network, this restricted Boltzmann machine, to represent a wave function. So here the idea is the following. See here now I have my neural net that has the number of parameters that I have is don't scale exponentially with system size, but scale polynomially. And then the idea is that I use the input of my neural net to be like a spin configuration, and the output will be the value of the wave function. Okay? Of course, there is still a gap here. One has to train this neural network, right? So this is the trick point. Okay? How to, let's say, determine this set of variational parameters. So now let's call these parameters, these neural networks, variational parameters, how to determine these neural network parameters, the variation parameters at the end, in order to be able to do this, right? To represent the wave function. And the answer for this is to use.
May I interrupt before he goes on?
Yeah, sure.
Yeah, I mean, I don't know much about this, but I mean, I have an idea what the H1, H2, etc. mean when you are talking about machine learning in, let's say, classical cases. But now you are talking as quantum machine learning, quantum neural nets, or whatever you're saying. So what would be the dynamic? I mean, can you give me an equation? Let's say, what would be the dynamic of a quantum neural node?
Okay. So here, let me say that the idea is to, maybe I don't listen right, but the idea is to use this in a classical computer, right? So it's a neural quantum state that represents a quantum state in a classical computer, but I'm not talking about, I don't know if you mentioned, but you enter, so the point is that I have, so the neural net, so far I didn't explain how, let's say, to set up the neural network, okay? I just explained that one can use the neural network to represent a wave function in principle, because the neural network is a high dimensional function and in principle, like a universal function approximator, okay? But now there is the key question, I think, is the question for the answer, and the answer for this question is the answer for your questions, how to set up my neural net, right? Neural network, how to determine this set of parameters, right? So is what people call in the machine learning community like training. How are you train my neural network in order to make this function like the wave function, right? And the answer for this is the variational principle. Unfortunately, I didn't put the equations, but I have in the end of the presentation. Maybe I can go there later. But it's to use variational principle, to use this artificial neural network as an ansatz, okay, for my variational principle, okay, right? And so this is what, let's say, the second element. And the third element of the method that is very important is that how to, let's say that we start my process. Let's say that I start with a neural network that is not exactly equal to my wave function. It's completely different, okay? It's just a random neural network, okay, that do this, okay, that has an input where S is the let's say spin up and spin down, and then I have as an output the wave function. So the other question is how to compute expectation values. One can like define like quantities. So here I'm defining this quantity, like the energy. In the energy, believe me, I didn't deduce that. I didn't show here, but the energy can be written this way. Okay, so here, so psi square is like the modulus square of my, let's say, random wave function. There's not still my wave function. I still have to optimize these parameters. But the key point is that in principle, this is still a many-body problem, right? You still have to run through all the, let's say, 2 to the power of n states. Okay? But the key point here is that I can do this stochastically. I can use Monte Carlo. Okay? I can do important sampling. Okay? I can efficiently explore the relevant states of as I do in Monte Carlo. Okay? As I do in Ising Model.
Before you were talking about using variational Monte Carlo. Variational Monte Carlo has a large bias, right? And there are only very few variational parameters because you have some opinion about what it should look like, which is not necessarily the correct one.
Yeah, exactly. I agree. I think the point of these neural networks is exactly to improve this bias, right? Because in principle, the neural network can, in principle, this of course, as everything is in principle, can model any kind of function, right? As long as I increase the size of network. So, so I'm not using any kind of bias a priori, right? So this in principle, of course.
So use variational Monte Carlo for what? For the input parameter, or this? I
use the variational Monte Carlo to compute let's say the neural network parameters.
Yes.
Okay,
and
so
then can you get away from that biased wave function or not?
So you can always increase the quality of the neural network.
I mean, in tensor networks, in some sense, it is also a variational calculation, but has an enormous number of parameters. So it's much less biased in that sense. I don't think we know exactly how biased it is.
Yeah,
but it's certainly much less biased than conventional variational Monte Carlo.
Yeah.
So can you get away from the restrictions of your initial opinion? Okay.
Because I think you don't put any initial opinion, right? So here we're using, so when you use like other kinds of ansatz for the wave function that you, let's say, that you put as an input physics, let's say, then we can introduce some bias. But here, of course, it's in principle, this process can break up. This we don't know yet if you can do this for like all kind of states. This is not known yet. But in principle, I think the main point, the main motivation to use these neural networks is that the neural network is a model that is a universal function, can fit any kind of function, as long as you increase a lot the system, you increase the number of parameters. Yeah, and then again, so it's exactly what we do. What people do is exactly what people do in variational Monte Carlo, right? As you mentioned, Eduardo. So basically, in order to implement the variational principles, we have a set of equations that I skip here, but I can show at the end of the presentation. And this set of equations depends on you have to compute quantities, and these quantities you compute stochastically, like I mentioned here. But then with this implemented the variational principle, I can update my neural quantum state. And then I can return here and can keep running this process until, for example, the variance of the energy, let's suppose that I want to compute the ground state, until the variance of the energy it's small. So you can do this. You can use some criteria to define when I reach convergence. But it's exactly what it's done in variational Monte Carlo. The only difference is that now I use this neural quantum states as my ansatz. All right, so I don't know if, so then the idea is that one can derive variational principle for both for the ground state, but also for dynamics. Okay? This was done a few years ago. Okay? In the context of variational Monte Carlo, there was no this neural network at the moment when these principles were derived for many-body system. So in principle, one can, of course, this will be an approximation, okay? Because my wave function, I have to use a finite number of parameters. So this is all right. So then, the idea just to mention, so this is so this work is basically I'm doing a summary of the work of Giuseppe Calleo that I mentioned before. But the idea is that now I want to use this method to probe this kind of correlations, okay? So dynamical correlations, so green function, retarded degree function in many-body system. So here we use like a protocol that was proposed to measure this kind of correlation in synthetic quantum systems. So you use exactly this protocol, and the idea is to perturb a system locally. Okay? So the idea is that you compute the ground state, with this method, and then you perturb this ground state locally, and then you will let the system evolve. Okay, and one can show that this equation here that expectation values of local quantities as a function of time, of course, now it depends on this green function. Okay, so one can derive this expression, but also there are other terms here that for the kind of models that we study are equal to 0, okay, because this model has like parity symmetry. So the models that I will show here has parity symmetry. So basically, I don't even need to worry about the system, but in principle, I can also compute with this approach. So this is the basic idea of the method. And then we can also use like fluctuation dissipation relations and compute spectral properties like this dynamical structure factor, for instance. All right, so let me show like the preliminary results that we have so far. So basically, we try to benchmark this approach with like simple models, like simple but like realistic in the sense that can be realized in this synthetic quantum system. So here's like the green function for a system with, let's say, 40 sites. It's a 1D system. Okay? And here is like the position. Okay? And here, like the comparison with exact results. And basically, we see that the approach starts to fail to times, but times that are relatively large. Okay, in the sense that we still can compute. So here's I use this fluctuation dissipation relation, compute this dynamical structure factor, and here's the whole spectrum of the system compared with the exact result. So this model you can determine exactly this dispersion relation. So then you can compare. And also we already extended that for 2D quantizing models. So here's like results for the 2D Ising quantum models. For the 2D quantizing, we still can benchmark with like small system size. So here's a system size with L equal to 4. But we can, like, with this method, we can reach system size that are beyond what we can do with exact diagonalization, with exact results. So here is like the spectrum of the 2D quantizing model for system size up to 10. Okay. This is like just to give an idea of some results that we have, but the idea is to propose a method to compute these spectral properties and response functions using this approach. Yeah. All right. Yeah. So then I arrived to the end of my talk. Before close, let me just mention some, let's say, directions that I'm pursuing. Some of them I'm already pursuing, some of them I plan to pursue in the near future. But the ideas, these directions try to use this machine learning as a toolbox for many body problems. So one is like to use these things that I mentioned in the first part, like about this intrinsic dimension, these statistics of distance, right, that we use to compute this dimension, to try to characterize like physical data sets, like experimental data sets. So there are also other things that I want to do related to try to relate that with an normalization group. And also another thing to want to do is try to using these data mining studies, like to try to shed some light or like to investigate, to explore the sign problem to see if, for example, if there are some manifestation of the sign problem in configuration space. Okay. So this is more like something that I didn't start yet, but it's some plans for the future. And also want to apply this second method that I showed before in the last part of the talk to simulate models for Rydberg experiments. More specific, try to analyze the prospect of topological phase in these models. All right, and with this, I thank you. So this is all.
Thanks, Tiago. So, Belita, you had a question?
Yes, I have a quick question. Tiago, when you showed some plots for diagrams for two-dimensional antiferromagnetic systems, you showed the experimental results where you said this is the wave function. But is it the wave function or the square of the wave function?
You mean this? I think you mentioned this figure here, Belita?
Yeah, you showed it earlier. Is it the same you showed earlier?
Yeah, it's same.
Yeah.
No, it's not. It's like let's say. So basically, our wave function is a superposition of different classical states, right? So then this snapshot is like a classical state of. So I did a projective measurement, and then I have a.
You have the orientation of the spins.
Yeah, exactly. So blue here is like spin down and red spin up. Spin up, yeah. Because the bright points is like the system is in an excited state. This is this Rydberg state. So you have this fluorescence image.
But in principle, you cannot measure probability densities, right?
Yes, of course.
You should not get the exact wave function. I don't think the wave function can be measured.
Yeah, I didn't mention the wave function. I mentioned snapshots of wave function. Maybe, so by snapshots, I mean these classical configurations.
For me, it's a projection of the wave function.
It's a projection of the wave function in certain in certain basis state, not classical state, basis state.
It's a reference.
That has a certain probability, of course. So basically the experiments, they have to do like a lot of repetitions, right? Because if they have to do any statistics. So what in this experiment, in this experiment, they did more or less 1,000 repetitions. Okay? So basically, we are trying to collaborate with Antoine Bravais groups and try to analyze the data that they generate in this experience. And what they send to us is like 0 and 1s. Okay, so it's like a data file with lines. Each line is like a configuration like that.
And then they don't show a snapshot. It's many snapshots, right?
Yeah, exactly.
Okay,
and then you do any statistics of this, let's say, and then you can compute relation functions, for example.
Okay, thank you.
Ignacio, you had a question?
Yes, I have a question. So maybe it's a bit difficult to answer, but nevertheless, I will ask. And it's related to what extent can you ensure that your method will work, or if you can hint towards problems in which it will work. So you look, I mean, the way you presented is that you have a set of wave functions and then you try and let's see if it works. And since we can benchmark in some cases, then it works. But of course, you could try now whatever wave function you want and do the same thing. And so the choice of some of these wave functions should have certain properties. And one property you mentioned is that, so of course, should kind of, I mean, you increase the number of parameters, then it should get better, right? And at some point exact, but of course it will get exact probably when you need an exponential number of parameters, and that's not useful. Yeah. And other properties you can prove mathematically that certain kind of problems, you will have an efficient description using that kind of wave functions or that kind of sets. And that's my question. So is there any case in which your wave function you can prove or you can show that will be efficient, so for some kind of problems? So in the case of tensor networks, we know that if you have local Hamiltonians and you have any equilibrium state, thermal equilibrium, you can prove efficiency, that the number of parameters only scale polynomially with the size of your system and not exponentially. But for the neural network states that are based on machine learning, can you find some set of problems for which you know that it's going to work, that is not like trial and let's see?
Yeah. I think the short answer is I don't know, like to pinpoint, like let's say general case, let's say a set of cases that I just need, let's say, a polynomial number of parameters to describe the state, not exponential large.
Like for example, we know that in 1D.
I think there are these equivalents with MPS states, right? Certain case one can, let's say, connect the two approach, right? But I think I don't have a general answer for that. I don't have a.
So maybe what you say. So of course, if you can efficiently simulate with your neural networks with a polynomial number of parameters any matrix product state, then you will be efficiently able to simulate anything that can be efficiently simulated with matrix product state. So the question is, can you, with your neural network, efficiently simulate all matrix product states?
This is related to my earlier question about variation in Monte Carlo, essentially, right?
It's very much related to what Eduardo was asking before, right?
Yeah, because the problem that there are like different levels of, let's say, issues that one have to address in order to answer a question. The first one is representability, right? If one can, let's say, describe the wave function with a number of parameters that is still polynomial with system size. But there is also the minimization problem, right? That is a stochastic minimization at the end, right? So.
Right, but let's assume that we forget about the second problem. It's a problem on top of that. I'm
okay.
asking about the first one.
Yeah, I would say that like states that one can connect with MPS, I would say yes. I think we still can. But I don't know the answer for this question, and and of course, there are also like examples of states that, but this is again is exploratory like results. It's like trial and error, as you mentioned, like high entangled states that we can examples of high entangled states that you can simulate with these neural quantum states that would be hard for a tensor network, right? So, but general proof for that, I don't know.
Right?
Yeah, I want to come back to a question I asked before, and is what is the physics of this minimum?
Okay, let me go to the.
I mean, and the question is there a way to relate that to the properties of certain correlators?
Yeah.
Or, you know, all of the endpoint functions.
Yeah.
To actually understand?
So the basic idea is that what to observe is that the key aspect is this distance. So basically, the distance also exhibit this scaling behavior. If I look at the statistics of distance, that let me go straight here. So this distance can be this again. I don't have a proof. It's just an heuristic argument. Can be related to correlation functions. Okay, so we can under some certain conditions we can write this intrinsic dimension is the inverse of the log of the second, the reference second year's neighbor distance, and the reference, let's say the average second year's neighbor distance, and the average first year's neighbor distance. And the basic idea is that one can, so here's the definition of distance. So here's Euclidean distance. Okay? So basically, the Euclidean distance depends on correlations. So these are a correlation between configurations. Okay? So this is not correlation, real space correlations. Okay? But what we argue, and we is that under certain conditions, one can write this kind of correlated in terms of real space correlation. So I don't know if was the index here. So I and J is the index of correlations, or configuration, sorry. And K is the index of the real space. Okay. So basically.
So, but this is the same position in space? Okay.
Yeah, the same, yeah. So this is what I'm saying. So the distance are.
Let me rephrase my question in a different way. Suppose you were in, I don't know, 14 dimensions, okay? Very high dimensions, so that mean field theory is essentially exact. In that case, you expect the probability distribution, even close to the critical point, to be a Gaussian by the central limit theorem. Okay, so how can you tell if you are in the central limit theorem or not, regime or not, from your calculations? Or how can you tell that the central limit theorem fails? This is very much related to the physics of the renormalization group, because that's how you end up with non-trivial distributions, essentially, and fractal dimensions and all of that. Is the failure precisely of the central limit theorem. So there should be, in your definition of distance, there should be a way to test for that.
Yeah. We didn't explore this direction. It's certainly something interesting. Yeah, so far I think, as I said, I think so this scaling behavior, as I said, is already contained in the statistics of distance. Let me show here. So for example, so here, so it's the Ising results and the XY results. So here's the distribution of distance, first neighbor distance, the whole distribution I compute empirically. And here is let's say the second moment of the variance of this distribution. So the variance already exhibits some scaling behavior. Also the first moment, the average of this also exhibits scaling behavior. I didn't show the results here. So I think the answer is that it's already, I mean, not an answer, but it's the starting point to understand this more deeply is that so it's the statistics of distance contain these correlation functions, real space correlation functions. But
okay, I think that's an important point.
Yeah, so this is also, this is something that I'm.
Otherwise, it's very hard to understand what is a minimum measurement.
So so this is also a thing that I'm working on now, is try to relate that more deeply with renormalization group. Okay, So the basic idea of this, the thing that I'm trying to do is try to see how these features of the data set, like the distance and the intrinsic dimension, change under a normalization group transformations. So for like simple models like 1D Ising model, we can do this exactly, and then you can try to answer this question like also for the 2D. So this is something that I'm working on to try to understand better this scaling, like using RG, more concrete arguments based on RG. But it's still work. That is still open question for me.
Mm-hmm. Okay, thank you.
Anybody else have a question? Okay. Okay, so thanks very much, Tiago. So tomorrow, I think it's at the same time, right? 11 o'clock in Brazil.
Yeah.
Very good.
Okay,
so thanks very much.
See you tomorrow.
Thank you everybody for watching. See you.
Bye.
Bye-bye.